What is up, fellas? Welcome back to my channel. This is Tony, aka One Leet One Day. If you're new here, this channel will do one lead code per day, following the pattern of topics or series. Basically, I'm going to be studying with you guys together on a lead code problem I have never attempted before, each day. You heard that right. There is no prescripted answer. We're on the same page here. But don't you worry, I got your back, and I promise that I will submit at least an average performance code at the end of each video. Here's a little bit about myself. I come from a non-computer science background, so I am no better off than most, if not all of you guys, in terms of coding knowledge. But that is okay. It is all about learning on the go. You can think of this video as first-person gameplay of cracking lead codes. And who doesn't like first-person gameplays, right? Right, so without further ado, let's start today's coding problem. Today is the fourth episode on Series 1, Everything About Dynamic Programming. And we're using a series of problems collected on the Leetcode website about dynamic programming. And today's problem is 746 min cost climbing stairs. So let's get into it. All right, here we go. Problem 746 min cost climbing stairs. If you remember, in a previous video we did climbing stairs, and this one seems to be a different variant of that just by looking at the name. It's an easy problem. Okay, so let's read the problem together. You are given an integer array cost, where cost I is the cost of ith step on a staircase. Okay, we have a cost for each step. It is interesting. Once you pay the cost, you can either climb one or two steps. You can either start from the step with index 0 or the step with index 1. Alright, you can choose from one of these two starting points and return the minimum cost to reach the top of the floor. Okay, sounds interesting. Let's take a look at an example. Example 1, the input is cost equal to 10, 15, 20, where 15 is underscored. And the output is 15. So how do we explain it? Well, um, we're probably looking at minimum cost as the title suggests. And if I understand correctly, the cost for the first stair is 10, and the cost for the second stair, if you step on it, is 15, and the cost of the third stair, if you step on it, is 30, is 20. And you want to reach where? You want to reach stair 3, right? All right, so let's see what we do. We start at index 1. Um, because we start on it, we will be stepping on it, and we will need to pay 15. Okay. Okay. So I think this is the right understanding. The first element in uh, the cost array, it means the zeroth stair, and then the second element is actually the first staircase or the first step, and the third one is actually the second. And where do you want to go? You want to go, um, I guess, past 20. So you want to go on to the third staircase, which is whose cost is not listed here. I guess the cost is 0 because once you reach the goal, there's no cost of reaching goal, I guess. All right, so just to visualize this, I mean, let's actually start drawing something. Here we go. And we're gonna just basically replay um, example one to increase our understanding. Now, to yeah, basically to solidify or verify our understanding, we're gonna put that first case here as an example, right? And the drawing, it should be like this. Let's see, yeah, um, staircases, right? Whoops, what are we doing? Right, to visualize this, we're gonna do one, two, three. Yeah, that's about it. Let's say this is 0, 1, 2, and 3. And for the cost, um, this is stair 0, and its cost is 10. And this cost is 15. This cost is 20. And this is where you want to go, right? This is where you want to go. So obviously, and we can start, let's mark possible starting points with a different color. Let's use green. Ah, let's use green to indicate start. Okay. Huh, interesting. Just use color, green, green, green. Okay. Now we can either start from here or we can start from here. And to get the minimum cost, we're going to choose to start from here. And what is going to be our trajectory? Well, let's just draw our trajectory using red. Yep. We start from here, right? We start from here, and we can take the stride of 2 stairs at once and then go directly to 3. So there's no additional cost, and the total cost C is going to be 15. And that is basically the first example, which we kind of animated. Yeah. And let's take a look at another example to make sure that we understood it correctly. Wow, this is a very high, pretty complicated staircase. There's six, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 stairs. Uh, all right. And and the optimal choice, which is underscored, is to take the 0th staircase and then jump, 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 no jump, and jump. Um, and then you can basically reach the reach the top. And the total cost is 6 because, well, you see, yeah, this cost array, it has either 1 or 100. Of course, you take the ones, and even when taking ones, you try to leap ahead as much as you can, so that you save the number of total steps um, to reach the top. Okay, um, so yeah, um, I think that makes sense. And do we want to visualize this? No, it's too much to draw, but I think we got the understanding correctly. So this is the problem. You're given a cost and you want to output uh, a cost array, and then you want to optimize the cost by producing the minimum cost for climbing the stairs. And here, remember, this is important. You take a look at the constraints of the problem scale. So the cost length can go from 2 to 1,000. Uh, and each individual cost can go from 0 to 999. So the problem, it could be pretty big actually, looking at this. Yep, and now we need to sit back a little bit and think what kind of strategies we can use for this problem. And because this is a dynamic programming series, supposedly dynamic programming is going to help us in making the solution more efficient. Uh, and uh, and because we're given a constraint, a previous trick that we have been using over and over is to, pre-compute all the answers that pre-compute all the scenarios that are possible, and just, in the main function, just look it up. But in this case, I think it's not a good idea because now this is almost like a continuous, although everything is discrete in terms of value, um, but uh, but the range is, it's too vast. I mean, it's a vast range from 0 to 999, and you can have between two steps, two stairs, and 1,000 stairs. So to combine these two variations, I mean, there are millions, I think, if not more, combinations out there. So it's not like a smart strategy to, pre-compute everything. So we're probably gonna give up that thought. And what else can we do? We can do like computation on demand. Maybe that'll help. How does that help? Well, let's say if we can we rely a complicated computation on some previous computations, right? That's something we want to know. Um, well, I guess each of these problem challenges can be different enough that there's nothing common that one can learn from one solution and then apply it to another solution, right? So yeah, because for example, if you're given a cost array of like 20 values once, and then in the next problem you're given a cost array of like 50 stairs, and the the cost for each stair for each step is like totally random. So there's nothing you can learn from one that you can apply to the other. So yeah, I'm pretty convinced that trying to reuse calculation from one solution to another is probably a dead end. So that leaves us um, with only one choice, that is to individually target each given question, and there's no knowledge sharing between questions because the total sample space is too large. It's scaring. So um, that is what we're gonna do. We're gonna just look at each individual um, uh, test case and then try to make that each individual test as fast as possible. Um, so what do we do? For example, let's see, can we just give ourselves like a baseline algorithm to do this? Um, well, we can start thinking, right? We want to reach the top. That means we want to get to either the last number in the cost array or the second to the last number in the cost array. Both would work, as we see respectively in example 1 and example 2. Um, and also we can start either from the first element in the cost array or the second element in the cost array. So those are possible options. Right. So I'm just thinking what kind of strategy we could be using here. Well, um, you know, let's start thinking about, not so optimal solutions first. I mean, we can just, travel every step here. that is going to give us the most costly way of climbing to the top. We're just gonna stand on each staircase, and you know, a little bit better strategy is to always skip stairs, right? To skip one stair and then to skip another one stair. So approximately you're just like taking half of the total staircases and go your way to the top. But that could be suboptimal, and it usually is suboptimal because you could be stepping on some of the more costly stairs rather than the cheaper ones. Um, and I am thinking now that I now that I start to have an ideal of it, I think we can we can propagate, the optimal solutions backward from the end, and then try to find the um, trying to build our way back to the beginning. And I think that's something I can rely on by using that. So let's start drawing something. I'm just prototyping um, an idea here, okay? And the idea goes like this. It's I think it's going to be based on a little bit of like dynamic programming knowledge, which I happen to have some. That is the principle of optimality, or sometimes called the Bellman principle of optimality. Let's just open up a page and let's take a look at what that is. Bellman principle of optimality, and we have a Wikipedia. There we go. Bellman's principle of optimality, and it says that an optimal policy has the property that whatever the initial state and initial decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. Um, yeah, it's not, by reading this sentence, it's not the best way to understand, but um, but um, but I guess we can demonstrate the idea using some kind of schematics or drawing. So I think what Bellman principle of optimality means um, in terms of in this case is that um, let's say we have first we need to have um, a stage variable. Let's just try to use black here. Yeah, so um, let's do like a mini walkthrough of Bellman's principle of optimality. Bellman's principle. Bellman's principle of optimality. So first we need to have something called a stage variable. Stage variable. It could be time, it could be distance, it could be anything of your choice. Um, let's just take the staircase example here. So the stage variable, it could be, um, you know, the number of uh, the number of the number of steps we've taken. So it could be step, right? And step, it could be like um, 1, 2, 3, 4, all the way down to n where we stop, right? Like and f, the final one, like and t, terminal one, or an f, the final one, right? So we we can just define our stage variable like that. It could be time if you're dealing with like a time sensitive sequence or something, um, which is often the case in optimal control, where you need to optimize a sequence of control signals uh, um, along time. But in here, our stage variable is step. That means you need to optimize your choice of your strides along your step. Meaning, like, for example, how many what's the stride for your first step? It could be one or two, right? And what's the stride for your second step? It could be one or two, and so on and so forth, um, until you actually reach your goal, which is either the last, which is either uh, this in this case, either stair uh, stair number two or stair number one. And once you reach either of those two stairs, so second to last and third to last stairs, you actually reach your goal. Um, right. So this is stage variable, and what it means, it's like a sequential list of variables that you will have to experience in your process. And then the goal here, right? We're dealing with the problem, right? Like the goal of this problem is to find your optimal sequence of like choices, right? So how do we define choices? Find optimal. So for control, we usually use U. So U1 optimal, we use the star to indicate that this is the optimal choice. U1 star, U2 star, uh, and so on, all the way to U and F star. That either minimize or maximizes the cost. In this case, we're gonna minimize the cost, right? Like so, let's choose J for cost, which is often the case in control literatures. Uh, that minimizes that, and then U U1, U2, etc. Minimizes that. So this is our goal. And how does the principle help us in finding these optimal sequences? Well, the Bellman's principle tells us um, uh, that if um, uh, let's say um, if we find like a sequence of control signals, for example, um, let's say UK, uh, and then um, U, UK plus one, and all the way to U and F. Um, yeah, it's just like K is K. Let's say K is greater than one. So we didn't start from the very beginning. Um, a um, it's just a partial sequence from somewhere in the middle of the uh, total number of steps to the end. If if this sequence if this sequence uh, um, is if I tell you, or if anybody tells you that this is part of is part of uh, an optimal sequence of U stars. If that is the case, then um, then op then any optimal sequence then any sequence that is claimed to be optimal will contain will contain this sequence. Let's call it uh, S of k, right? Contain sk. So what does this mean? Well, it means that if we have a snippet or like um, a fraction piece um, of a sequence that is claimed to be part of an optimal sequence, uh, then any full optimal sequence of the same problem will contain uh, this self-claimed um, um, snippet of optimal control sequence. Yeah, it's a little bit counterintuitive, I know, but this principle it can lead to a great algorithm of building up optimal sequence from from the last step backward to the first step. And let's just verify that this is actually what the Bellman's principle of optimality is, making sure that I didn't just uh, mm, come up with the wrong expression. So principle of optimality says an optimal policy has the property that whatever the initial state and initial decisions are, the remaining decisions must constitute an optimal policy with regard uh, to the state resulting from the first decision. Um, okay, it's a little bit different. It's a little bit different. So it's a little bit different from my understanding of it. So let's see if they actually are the same thing. So an optimal policy has the property that whatever the initial state and initial decision are, okay, whatever the initial state or decision is or are, um, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first. Must the remaining decisions must constitute an optimal policy with regard to the state uh, regarding with regard to the state resulting from the first decision. Um, all right. Okay. So let's see. Let's see how this makes sense. Let's see how this makes sense um, with our finding or our basically with our statement here. Um, right. So I'm gonna mark this as like my understanding. Uh, my understanding. Mine. Uh, yeah, just say understanding uh, of BP, Bellman's principle. Um, so, um, oops, yeah, I think I lost connection to my pen for a minute. Uh, there it is. All right, so let's just extract from my understanding and an expression that expresses uh, the Bellman principle idea. So what I mean, or what I recall, is that we can we can build our optimal cost to go, like optimal cost to go. This is the concept optimal cost to go. Cost to go where? Go to our final goal or like to reach our goal. Um, and we're gonna define that C as C. uh, optimal, right? C optimal, um, and it's a function of the state where you start. So you're gonna start the state, right? Like the state variable, it's gonna be x. Let's use x for state variable. Uh, right, and that's pretty much it. Uh, so what is x? I mean, in the staircase problem case, our x it it is basically representing which staircase we're on. So, for example, it could be 0 for when we are on the 0 staircase. It could be 1 for when we are on the first staircase, or it could be 2 for when we are on the second staircase, or it could be 3 for when we are like on the top, over the top now. So those are our states, right? Um, and uh, And basically this C here, it's kind of a cost, and this is our optimal cost. So we can say this C is actually C star, our overall C star when we start from the beginning, either from 0 or 1. So yeah, um, so optimal cost to go. So now X, um, it in a more general sense, it could be any of these 0, 1, 2, 3. So optimal cost to go. Um, let's say defined a we've found an optimal cost from the state X to uh, the final state that we need to be, which is I think so. This is our final state. So this X is like our X F that we need to be in the end. So uh, this optimal cost, let's say um, this is already found, right? Uh, yeah, it is already found, so we don't need this equal sign. And we can use the Bellman principle um, to basically um, calculate more optimal cost to goes, uh, earlier in our stages, because we're calculating. Remember, because we're calculating backwards. So so here's how it goes. First, we calculate like C star all the way from the very last state. So it's going to be XF. And of course, this is going to be 0 because if we're already at the last state, we don't need to pay anything to go any further, right? And now we're going to see uh, what are like the states that can possibly reach the last stage in one go. So that leaves us with two possibilities, right? So either, um, yeah, let's just build a kind of like a tree here, XF. Um, so because we only have two possible strides, we can either do one stair at a time or two stairs at a time. So uh, this is XF. Let's say this is like XF minus 1, right? This is like uh, XF minus 2. So we can either go from XF minus 2 or we can go from XF minus 1. And since we already worked out that cost to go for the last final state is 0, we can then move on to calculate C star of um, XF minus 2 and C star, um, well, let's write it down here. C star XF minus 1. And how do we calculate them? This is where previously um, we talked about the Bellman's principle. This is what the Bellman's principle is going to help us with. So when we want to determine what is the optimal cost to go um, at an earlier state uh, prior to the last state, then we can, because we know that if a subsequence uh, is is part of an optimal sequence, uh, then any optimal sequence will contain the subsequence. Well, this is not like a very full, complete description of it. What this means is that actually, yeah, we'll come to like a better summary at the end of this video. But for now, let me just tell you that if you want to work out the optimal cost to go from x f minus 2, then we need to basically find um, find all the possible pathways from this xf minus 2 to xf. That is in this case from stair 1 to stair 3, all possible ways. Uh, and then find out uh, the uh, the least of them, right? What do I mean? So you're gonna find the minimum of all possible ways to go from 1 to 3. Uh, so that could be, let's say, if you go from 1 to 2 and then 2 to 3, that's one way of doing it. Or you can go from 1 directly to 3. That's another way of going it. So we have uh, um, two possible two possible options here. So that is, let's write the first one, right? So it's gonna be a first one and then a second one because we only have two choices here. And the first one is uh, if we take one stage, one step, one stair, and that is, and the cost of that, I think it's you know, uh, from um, from xf minus 2, right? So how do we write this? Like a one-step cost, right? So uh, for one-step cost, I'm going to use um, the symbol A because later on we're going to call it the arc cost, just the one-step arc cost. A from x from minus x from x f minus 2 to x f minus 1. It is an arc cost of that. Uh, yeah, f minus 1. And then, of course, the remaining cost of going from f minus 1 all the way to 3. And that is nothing but c star of xf minus 1. And this is the essence here. So we're going to pause a little bit and think about this, right? The cost of trying to choose uh, the one step, right? So once this is like the our cost of taking the one step, taking the one step. And then after taking the one step, you end up in the situation uh, of staircase 2, and definitely you still have to make uh, subsequent decisions. But since we have defined, C star as the optimal cost to go, uh, then according to this Bellman's principle, um, any optimal sequence that follows state 2, has to be the exact optimal sequence that was claimed, which is the C star here. So this is basically a static storage. So once we worked out what C star x f minus 1 is, we can store it in a storage unit, and then just just look it up whenever we need to look it up. So um, anyway, so the first choice of going of starting at x f minus 2, which in this case is 1, um, and then also taking a one step as the next step. Um, for for this situation, the sum of these two terms is um, the optimal cost of this situation according to this Bellman principle. I know you could be super confused right now, but don't worry. I mean, we'll we'll come back to a better summary later. But for now, please just stick with me, and we'll get through this. So for the second possibility, when we start from x f minus 2, is to take a two staircase stride uh, in the next step. And so we just write that down, two step, and 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 from here, because we have instructed the control or like the decision for the next step, we can calculate the arc cost of jumping two steps from state x f minus 2. Uh, and then we're gonna also denote that arc cost with the letter A for arc, and this is f minus 2. And after that two-step jump, where do we land? Well, let's see. We go from stair number 1, jump, we go to stair number 3. So we'll actually get to xf, which is the final step that we want to be at. And of course, just for consistency, we're going to write the optimal cost uh, at state of xf, which is 0 according to the definition of a final state. Right. So this is our expression for c star xf minus 2, and similarly we can do the same for c star xf minus 1. And it's going to be actually simpler because yeah, we can take a 1 if we are at x minus x f minus 1. The only I guess viable option is to take a one step stride, because if we take a two-step stride, we're gonna land on staircase number 4, which is non-existent, uh, which we don't know if that state is acceptable or not. um, and so we're only gonna have one, actually just one choice. That is to take a one-step stride, and we're gonna have an A, means arc cost, to go from xf minus 1 to xf, and remember to add to it the uh, optimal cost to go the of the resulting state, which is c star of xf, which is 0. Um, right, so this is how we build, like, step by step, actually we should say it this way, because xf minus 1 is like uh, is the closest state to the final state. So we actually go from the last state, and then go to calculate xf minus 1, and then we calculate the optimal cost to go of xf minus 2, and then we do it all the way all the way from this all the way to the first state, or what we call x0, right? So um, and then we will have built like uh, a list of optimal cost to goes for all the possible states. And after that, we can just take a look at the optimal cost to go of state zero, and then the optimal cost to go of state one, and then just find the minimum between the two, and that will give us our final answer to this staircase minimum cost staircase problem. I I am now pretty sure that this can work. And I know that you must be confused by my partial explanation of what Bellman's principle is, because I have a little bit of a struggle trying to, make peace between uh, this this verbal definition of Bellman's principle and, the Bellman principle that as I remembered it. So we'll resolve that later, but please just now stick with, I guess, my derived expression for the optimality, the Bellman optimality here, and then we'll take this, implement this into code, and see how it works. All right, so let's go back to coding. Um, Again, we're going to use the Jupyter Notebook or Jupyter Lab for our IDE, our Integrated Development Environment. Uh, we're gonna be prototyping our code from there. So we're gonna copy the problem description, uh, paste it into our prototyping code. So this is minimum cost climbing stairs, right? So let's just take that name, take names, kick ass. And we're gonna create a new notebook with the name of um, oops, um, what was the number of it? It's number 746, Leet 746, right? And we're gonna write down its name here. And also we're gonna include the problem description here. And we're gonna give an example here as well. So the example, it better be in the code format. There we go. And now we're gonna basically copy and paste the template that we are given here in Python, and we're gonna build it. All right, so let's first build some test cases. Uh, Test cases. Let's say we build our solution class object, and then we want to print uh, some of the answers. Uh, yeah, let's just um, take the template from a previous problem to keep consistency here. We're gonna first say we have an input and we're gonna expect some output. And since there is a constraint here, we actually want to stick to it, and we're gonna actually modify it here, constraints, to include the constraints. Right, so those are the constraints. There we go. Um, so the smallest length is 2, and then Right. So input um, cost length. Right. So it's actually an input array. What if we do, uh, let's just say 2 and 5? What is expected? Well, if it's 2 and 5, that means uh, at stair 0, we have a cost of 2. At stair 5, we have a cost of 5. And of course, we're gonna step on uh, the cheaper one, and then we're gonna just do a skip to get to the top. So that's what we expect. Um, let's do another one. For example, if we have 2, 5, 1, what do we do? Well, in this case, obviously just by inspection, the best strategy is not to land on uh, this one first, but to land on this one first and do a skip, uh, and then just move one stair up, we'll reach the top. So we're going to be expecting 3 here. Let's just do one more, okay? Print input, let's say randomly 4, 1, 7, 3. Um, right. So in this case, let's see, we definitely want to be stepping. Let's make it actually smarter. Let's make this 12. So this will be actually more interesting. If we step on the second, the second one here first, step on number 1, then um, we can do one of the following. We can either do a one step and then we go to 7, or we can jump and we do a 2 step when we go to 12. So obviously the smartest move we can perform here is to take number 1 first, jump to no jump, and then move to 7, and then perform a jump, and then we'll reach the goal. So for this we're expecting 8, right? Because if you take the the zeroth stair, and then you can either move to 1, which is cheap, but then you still have to face the same choice of either go to 7 or 12. That's going to be costing you a lot. Or if you jump from 4 to 7, that is already very expensive. 4 plus 7 is 11. And if you perform another jump, you still have a cost of 11, which is greater than 8. So the smartest strategy for this is like just take 1 and 7 and then do a jump. Right. So I think we're good with the test cases. Now let's build our solution. Main cost climbing stairs. All right. So how do we how do we do this? Well, for building a um, excuse me, for building a dynamic programming solution, um, we need to have the following components. We need to have a storage unit that stores the optimal cost to go. So I'm gonna actually create such a storage unit, storage variable. I'm gonna call it CTG, and do I initialize it? Well, then that brings us to the question of what kind of data structure we want to use. Um, Naturally, from previous episodes, we knew that if we're just doing lookup tasks, dictionaries is probably the best choice in Python. So we're gonna stick with that. We say it's gonna be a dictionary, and this is like storing optimal cost to go, cost to go from state, X from state X, and the keys are strings uh, with the state, strings converted from integer. That is kind of useful because we can just use the staircase number as our state, and then we convert it into string to form the keys for our dictionary. The reason why we need to convert the integer into strings is because um, like the keys in Python uh, has to follow the format of Python identifiers, and Python identifiers cannot start with numerical numbers. So we're better off just using strings converted from integers. Right. So that being said, we can move on to our design of the main algorithm. So the main algorithm um, should go like this. Uh, we're given a cost, and it's a list, right? It's a list of integers. Um, so there's a few things we need to think about this. The number of elements in the list actually stand for the number of staircases, and the number of staircases, it kind of signifies um, the number of stages we the max number of stages we can have in our staircase climbing problem. So what that means is if you stick with this if we stick with this stage variable notion, we need to find our NF, right? We need to find our NF, uh, and then and then we go backwards to the first. So maximally, how many steps can we take? For example, if the yeah if the cost the cost matrix is like this, right? The cost array. For example, in this case, when the number of elements is um, 3, uh, we can maximally take how many steps? We can maximally take 1, 2, 3 steps, right? It's the same as number of elements. Um, right. So, but actually, this stage variable, it's never explicitly shown in our cost to go matrix. So, um, so I guess we don't really need to explicitly express NF. Um, but we do need to somehow, I guess, um, give the label, uh, give the labels for those x's. Uh, and naturally in this problem, um, we can just use the indices of the staircases as our labels for our states. In this case, it will be uh, 0 turned into string, and 1 turned into string, 2 turned into string, and 3 turned into string. Yeah, so it's going to be actually four of those. Yeah, 4 states. We're gonna have 4 states. So uh, let's let's start a new page and walk ourselves through that process. Okay. Um, let's just take the let's just take the uh, take this, for example, we're going to still take everything from here, and we're going to copy it, right? Copy. And then when we move to a new drawing, we hope to paste it. Yep. And here we can continue with our uh, dynamic programming approach and CTG, and we have a list of states, right? So let's say our list of states. This will be so our list of states. This will be easily 0, 1, 2. And we'll add artificially a number 3 to represent our target state. Okay, and list of states 0, 1, 2, 3. Right, and this is like can be read from the total number of elements from the cost, and we can then start to start calculating our CTGs, cost to go, right? And when I say start calculating, we definitely start from C star of the last one, so C star of 3, and then we go on to calculate C star of state 2, and so on and so forth, all the way until we arrive at uh, let's say state C of 0, right? So that's the end of it. So calculating CTG. This is our sequence of calculating our CTG, and this is our next step. And then of course we have another step of compare C star of 0 as well as C star of 1, and the take the minimum, because we're minimizing our cost. It only makes sense to minimize that, right? So we can abstract this entire process into um, 2 steps. One is that, and 2 is this. One is calculate CTG. So we'll have an array of CTGs, and for this, we'll have uh, we'll just compare that and take the minimum. Right. So let's just, oops, what is this? I think the thing got a little bit messed up. I don't know what those are, but yeah, somehow this got translated into a weird, okay. All right. I think this text tool is a little bit weird. So we'll use simpler expressions to make sure I don't trigger that weird behavior. Right, so this is our calculation sequence. And I just mean that we need to start from the last state, which is the end state, and then we're going to go backwards to the initial states. Right. Yes and yes. Right. So let's go to our implementation here. And so how do we do that? We're going to convert this cost array into a list of CTGs, and then perform the minimum operation. How do we do that? Well, I think this is going to be like a for loop structure because we are uh, going backwards, right? Because looking at this chain, it's like a for loop. So let's start with that for loop. Um, so actually, we do need to use a variable to represent the total number of elements uh, in in our uh, in our cost matrix, in our cost array. So that's the number of stairs. Um, the total number of stairs, um, we can use the length function and cost. That's the total number of stairs, right? I think yes, but it starts with 0, right? So it should be this plus 1. Stair starts with 0. Just remember that. Just in our case, we have 4 stairs. One is a virtual one. Yeah, but we still assign a cost to go for that virtual one. So there we go. And um, now let's build the for loop for, I guess, k in range of n stair, right? Well, again, let's just test the behavior of range. What is range 3? To see what is range 3, you need to build a for loop. In range 3, print I. So it's like 0 to 2. So in our case, yeah, we're gonna do for k in range and stair, and it's gonna bring us. So for example, if the length of our cost is exactly like what we have here, which is 3, then n stairs is gonna be 4. And then for k in range of 4, it's going to go from 0 to 3, which makes sense. So that's correct. So in this for loop, we are going to perform what the cost to go calculation. And this cost to go calculation is going backwards. So really we want to, okay, go backwards. So we definitely need to do the range in reverse, right? So let's see how do we do that. Python range reverse range. Um, right. How do you do a list with the reverse order? So people say use reverse range. Uh, if you want to be if you want it to be a list, um, you can do that. Or if you want to use range to achieve the same result, you can use always parameters start, stop, step. Right, I think this is what we wanted. So if you want it to go from 5 to 0, we do 5 minus 1 minus 1. Right, that's I think what I need. So um, we actually go from n stairs. So number 3. Wait. We're gonna have 4 stairs, right? Right, so n stairs is gonna be 4, but we're gonna start with instead minus 1 to being 3, and then all the way down to minus 1, and the step is minus 1. Yes. So now um, we better, yeah, take a note. Go backwards from n stairs n stair minus 1 to 0. Yeah. So calculate cost to go, and that means we're going to add something into the dictionary, CTG, uh, and the key is going to be a string version of the integer k. And what is the value of it? Well, um, before we use that recursive relationship, let's start by filling in the default value for the last step. So CTG of string of n stair minus 1. This is going to be 0, right? So we're going to say initialize CTG of the final state, yeah, the final state. Um, and because that is actually initialized, so we can actually go from n stair minus 2 downwards, right? Hey, mm, right, it makes sense, right? It makes sense. Okay, so now we go from CTG. So now we can apply our backward or our recursive relation here. And what is our recursive relation? We're going to take this equation here, and that's going to be our recursive relation, right? This one here. We're going to copy it, and we're going to go to our next state, yeah, here. This is our um, recursive relationship. Yep. We're going to calculate that using the recursive equation below. That's what we mean. And this is the recursive relationship we have. And yeah, so that is how we do it. But we now want to kind of like express it in a more code-friendly way. So let's say if we can rewrite this in a more code-friendly way. Um, yeah, so let me try that. Or, yeah, we're just gonna rewrite it. C star. Let's say we're given a k, right? Because that's what we have in the code. Um, but just one second, we're gonna have, you know, a string of that. Because now this is like a dictionary, so I'm just gonna use um, strictly the Python syntax here. Uh, and we still need to do the minimum. Wow. Okay. So, uh, is there a minimum function somewhere we can use? Right. Let's look it up because we need to do the minimum function. Uh, Python minimum of two values. The min method. Python method min returns the smallest of its arguments. The value goes to the negative infinity. Okay, so there we go. Yeah, it's just a min method. We can use that. So that's fine. That's good. We're gonna do a min function, and then the first element in that min function is gonna be this one here. Taking one step for the current stage for the current state. And so what is that A here? That A, for that A, we're gonna have to look up, excuse me, what is the cost of stepping onto the next stair next to this. So yeah, we're gonna be looking at our cost, right? There's like um, the cost list, and which one are we looking at? It'll be k plus one, I think, right? It'll be k plus one, meaning the next stair, next stage, uh, yeah, next staircase, starting from k. Again, our k here, um, it is an index that starts from 0 all the way to the last one here. So I think it's consistent. And plus what? Plus the cost to go of uh, of that state that we are landing on. So it's going to be uh, right, the CTG or C star um, of what? Of STR um, K plus 1. Right. So that is the first value. And the second value would be the two-step uh, um, action choice. So if we take two steps, that is if we take a jump from the current state, we're going to land on um, staircase number k plus 2. So what we're going to do is to look up the cost of stepping onto that by saying cost square bracket k plus 2. And then we're going to also look up the cost landing onto that state, which is C star of string k plus 2. Right. And then remember to return the bracket. Okay, so this is the expression that we want for our Python code. Of course, C star is CTG in our actual code. So let's do that. Yeah, let's do that here. And our CTG of that is min of cost k plus 1 plus CTG string k plus 1 or cost of k plus 2 plus CTG of string k plus 2. So that being said, let's close the bracket here. I think we just did that. Um, but is it gonna work? Because it looks like we're using two steps here. We're using two choices here, and we only initialized one of them. That could be creating a trouble because um, when we're at the second to last state, we're gonna be asking, then this is gonna be like the last state, right? Which we have initialized, but then it's gonna also ask for this, which is non-existent. Okay, this one is non-existent. So maybe we should initialize 2 CTGs instead of 1. And that'll make our life easier. Stair minus 2. What is this? This is like the arc cost um, of that of that um, of of standing onto the final state, yeah, which is 0, and then plus the CTG of that, which is again 0. So, you know, this thing here actually doesn't exist um, because yeah, this won't exist. But theoretically, that is what it is. Uh, so what are we gonna do? We're gonna um, because we know this is 0 and it's also 0. We just give it directly 0, okay? Yeah. So initialize um, initialize CTG of the last two final state. Yeah, okay. So then we can go from there to 0. Yeah, so um, let's see if this actually work out. If our cost has a minimum length of 2, right? Because our cost can have a minimum length of 2. That means then the length of cost plus 1 is going to be 3. So that's 3, right? So this is going to be 2. This is going to be 1. And then we're going to start from 3 minus 3, which is start from 0 down to 0. Yeah, we're going to be calculating CTG of 0, which makes sense. So I think this is going to work. Yes, this is going to work. And right, that's pretty much it. So what do we return? I think we just did everything we are supposed to do for this step. Of course, next we're going to have to choose the minimum between CTG of 0 and CTG of 1. So we're going to return the minimum between uh, this and this, right? Exactly. So I think that's it. I think that's it. So let's try it. To give it a try, right? Um, excuse me. Print s dot this, um, and then given that input, right? We're just going to be building our test cases. 251 for this one here, and it'll be this one here. Right, let's just calculate it. Calculate it. Huh. Okay, some error is there saying that CTG is not defined. Okay. Right. CTG is not defined, but I think I should have defined it already. I mean, we created a solution class, so by default it should initialize this thing here. So why is it not initialized? I'm not sure about that. CTG. This is kind of weird, but let's actually start the debugger and then just do that. Let's take a look at what we have. Self CTG is a dictionary, and it doesn't have anything in it. Um, and if we step, we're given an error. Name CTG is not defined. Huh? Why is that? Name CTG is not defined. Maybe we're using a wrong syntax for adding um, elements into dictionary. So let's look that up. Python, um, like say append dictionary. How to add value. Um, how to append an element to a key in a dictionary with Python. So append you can do a dictionary and then dictionary name append guru address append Mumbai age append 30 accessing element of a dictionary deleting elements. Right, let's just say add element to dictionary. How to do that? Right, you just do this, which is which I think is what I did, but somehow it's not allowing it, which is weird. So let's just do some experiments here. We're gonna do CTG. Uh, yeah, we're just gonna use C is like an empty dictionary, okay? And then C, we're gonna do key one equals to 0. Let's do that, and let's just print C out. Let's see what C is. Right, it does work. So how come that it didn't work in here? Oh, again, sorry about that. This is again another common mistake when using, object-oriented programming. You definitely need to add the self here. That was my bad. I mean, this is such a common mistake. Um, I make all the time, and I apologize for that. I'm going to add a label, a time tag in this video just to show people, skip this part. This is me trying to figure out what the bug is. Uh, and you can totally skip that if you don't want to, go through this entire 10 minutes just to find out it's a really basic, stupid mistake. All right, so I did just that. I'm going to make sure that everywhere, even in the documentation or comments, I'm doing the in the right syntax. So let's do that and do the test cases. What? Um, List index out of range? Really? Okay, let's see. Um, so we have a cost list, right? And you're saying that we're doing it out of range. Um, well, this is time, when a breakpoint is going to be really helpful. And we're going to just do that and do this. All right, here we have the breakpoint. Let's take a look at where we are. We're on this line 18 right now. And what is cost? Cost is a list with 2 elements. The length is 2. So k, what is k? K is 0, right? Okay, so if k is 0, and if the length of the cost is 2, let's take a look at our CTG. So our CTG, we already had a CTG of 2, which is the final state. Yeah, I can concur. And then the CTG of state 1, which is, the second staircase. I can concur. And then we definitely just need to, we basically just need to work out CTG of 0 here, which is totally making sense. But according to this expression, we're gonna need cost of state 2, which is not defined, in the original cost array. So I have an idea. Let's just extend the cost array into a larger one. Like we can extend it. I'm going to add the cost as 0, right? So yeah, I think I'm going to do that. Now what I'm going to do is to not use debug, but stair starts with 0. Yeah, I'm going to cost append, right? 0. Is that how list append works? Python list append to the end. Append to list, step-by-step guide. Shark, dragon, bear, cat, giraffe. And then if we append a meerkat to our list. Okay, I think that's what it does. That's what we are supposed to do. So, yep, append 0. So what we're doing is like we're appending the cost list to represent cost of the virtual last state. Yeah, so that's what I'm doing here. And I'm going to try it. Ooh, Okay, we have some answers, but not quite expected. Right, so we have some answers, but they're somehow a little bit unexpected. Um, let's see how and why. And here we're expecting 2 because we definitely need to step on something, right? Um, well, I think like this is missing like the 2 value, and this is missing. This is missing a lot, and this is missing, I guess, 1 here. Right, so going back to the logic here, let's say if we look at the first test case, 2 and 5, we're expecting 2. So the cost, the first cost is going to be the cost of stepping onto the state 2. And um, you see, when we're returning these things, they are not accounting for the cost of taking them. Right, so yeah, because you definitely have to take into account of stepping onto that first state. Um, right, so we need to definitely add that to it. 1 plus that. Yeah, this will make sense. This will make more sense. Because stepping onto that very first state you choose is also going to cost you something. Yep, and there we go. I think this is like a good pass. So now let's see if we can take this entire definition of our solution back to Leetcode and run it. Right. Solution is correct. Let's see if we can run multiple test cases. Wow, this is really taking some time. Meaning our code is probably not ideal. Well, it's actually not bad. 18 millisecond. So let's just submit and see how good we do, okay? Wow, 107 milliseconds for this. So our runtime is really bad. Memory usage is okay, but our runtime is really bad. Let's try it again. Okay, this time it's better. But still, our runtime is below average. Our memory usage is really, really good. Better than, most people. Let's just try to submit it again. Yeah, again, this is even worse. So I think we can conclude that this current version of solution we have um, is good in memory usage or above average, but pretty bad in terms of runtime. And that makes me wonder why, because we have used our dynamic programming correctly, but it is still slower than most people. And it is the solution peaking time now, and we're going to look into a number of the solutions that people provide. Okay, so there's an overview, and we have a few approaches: bottom-up dynamic programming, tabulation, and Python 3. And let's see, this is similar to ours, I think. Uh, and approach 2, top-down dynamic programming, recursion, and memorization. Now this is probably going to save us some time, maybe. Recursion memorization, right? Extract nodes. Complexity is good. Bottom up, constant space, right? Complexity is good as well. All right, so there we go, there we go, there we go. So I think these solutions are definitely worth looking into to basically improve our code. And our code that we have here is basically the bare bone version of dynamic programming uh, that uses this min function to to work out, the minimum cost to go for each step. Um, Similar to approach number two here, I think, or number one. Uh, Approach number one. So if you look at the syntax here, uh, so for this solution, if we take a little peek into it, um, the, let's read this comment here. The array's length should be 1 longer than the length of cost. This is because we can treat the top floor as a step to reach. Yeah, that's exactly what we did, right? Like we appended our cost array. And what they did is that they initialized minimum cost as an array like one length longer than the length of cost. I'm basically appending the cost matrix, the cost array, to represent what we want it to be. All right. So that means we're modifying the cost array. Yeah. And then start iteration from step 2, since the minimum cost of reaching step 0 and step 1 is 0. Right. So you're talking about, initializing the first two as 0. I did that explicitly as well. And then you have a for loop, um, range 2, length cost plus 1. You're actually going uh, way up. Like you're going in forward in the forward direction, while I'm going in backward direction. Take one step is minimum cost I minus 1 plus cost I minus 1. That Yeah, minimum cost. This is like the cost to go that I have, and take two steps is minimum cost uh, I minus 2 plus cost I minus 2. Yeah, this is like this one here. Um, and minimum cost of element I, is the minimum between these two. So you have a min function, and that's what I have here. So these three lines basically is equivalent to my one line here. And you have a for loop, I have a for loop, but the difference is that I go backwards to build it from, the last state all the way to, uh, the first two states, which is like the bottom two staircases. But what you do is that you build it um, from the first few states all the way up, and then you return that. But somehow I I don't believe this is the right calculation. Um, but it must be. But you know, this is quite weird. Let's actually, try copy this and see if it works. I'm just like disbelieving it right now. Um, let's just use that solution, run code, just run the code. Okay, is it running? Syntax error. Okay, so this is kind of like a, is that a Python? Because it looks like, yeah, even, I don't know. There's a syntax error. I don't know how, like this could be, okay, Python 3. Right, it's Python 3. Now let's run the code again. It's correct, okay. Let's try more test cases. Also correct. Let's submit that and see. Oh yeah, so it is definitely faster. Wow, Python 3. Hmm, this is actually quite new to my belief. Let's submit it again and see. Yeah, it still beats my code. Memory wise, maybe not, but runtime wise, it's definitely faster than mine. So I'm in kind of like a disbelief now. It's hard for me to, kind of like take this in of why it works, because to my belief, you have to go backwards in order to really take the Bellman principle to the correct understanding. But you seem to actually perform this kind of uh, co cost to go calculations um, in the forward direction, and then that you return -1, which means it's like the last element. Oh, okay, okay. I see. Okay. Now I understood, I think, fully what this is. It is still a backward operation, but, you're just treating the last element as the first instead. So you're reversing the staircase as well as reversing um, the minimum cost array. So, the reverse of the reverse is the correct order. So I think this is like identical to mine um, in a way. Like if you look at my Python code, right? Where was it? Yeah, I have to copy paste again the Python code here. Run code works, right? So it works as well. So my Python code here, um, as you can see, it's the same as this Python 3 code here. The only difference is that you reversed um, the order in the for loop, and you also reversed the order um, of your cost to go array. So when you are looking up the last element in your minimum cost array, I am looking up the first element, you know, in my the first two elements, actually the minimum of my first two elements in my in my cost to go array. So hey, if you look at this, this expression and as well as this expression, isn't that, I mean, the same? I mean, yeah, it's almost like you're doing the -1 thing here too. Yeah, isn't this like simply the -1 here too? Uh, yeah, like this is like CTG -2 minus yeah, minus 1. So yeah, I think even this expression is similar to this expression of mine here. Uh, so in terms of syntax, it's exactly the same thing, but how come that mine works less efficient than his? Is it a a difference of like Python 2, like Python versus Python 3? I think maybe, but anyway, I do believe that my answer here in Python is similar to the solution approach number one, which is bottom-up dynamic programming, tabulation. All right, so I think that concludes our today's work, and I'm going to stop here. But here is today's summary. We looked at a minimum cost climbing stairs problem, um, and we worked out our um, recursive uh, equation to calculate the solution that we want. And it turns out that we applied, um, you know, the um, Bellman principle of optimality, at least a version of it. Um, so we still have a little bit of conflict between, I guess, um, this my version of interpretation of the Bellman's principle and what's written here in Wikipedia. So in a way, the definition of the Bellman's principle of optimality is still a little bit of a blurring. Um, as I promised, I'm trying to I will provide a clarification of that and what all this means. Um, so um, yeah, let's try to do that now. Actually, let's try to do that now. Um, so we are trying to reconcile the different definitions um, between what I have here and what Wikipedia has here. Um, okay, let's actually read a little bit more on the Wikipedia page on this line here. As suggested by the principle of optimality, I'm going to make this text larger so it's more readable. As suggested by the principle of optimality, we will consider the first decision separately, setting aside all future decisions. Okay, we will start afresh from time 1 with the new state 1, x1, collecting the future decisions in brackets on the right. The above finite horizon decision problem is equivalent to max. Okay, this is like a maximization problem, maximizing reward as opposed to minimizing cost, but they're equivalent in a way. So max of this curly bracket, and what is that? It is f function um, plus some kind of a beta factor times this square bracket, which is what? Uh, Another max of at from t equals to 1 to t equals to infinity of sum of all the subsequent costs. Okay, so I think this lengthy square bracket means the optimal cost to go or optimal reward in this case because you're maximizing a reward. So this is like the optimal reward to go from where? Um, from from the state resulting as a result of state x0 and action 0. So you may land at some state x1, and this square bracket is the optimal reward to go um, from that resulting state x1. It's similar to my expression here, right? So we're basically minimizing the cost of all possible actions since the state x f minus 2. And by all possible actions, I mean either taking the one step or taking the two step. And so it's similar to this expression here. Uh, but still, this sentence written by Bellman is still a little bit, abstract and blurring compared to the recursive mathematical equation for cost to go or, reward to go. So let's just read this sentence again to see if it makes sense now. So the principle of optimality says an optimal policy has the property that whatever the initial state and initial decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. Okay, so I guess it starts to make more sense now, now that we have gone through all this. So all that means is that the optimal cost, for example, the optimal cost starting from the state x f minus 2, it has to be, according to this sentence, um, so if the initial state is x f minus 2, then and whatever the initial decisions are, meaning that either we take the one step or we take the two step, it doesn't matter, um, then the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. And that is what these C star optimal cost of goals are. So the remaining, meaning um, remaining cost besides the arc cost here, they must be like uh, they must be like consistent stored optimal cost to go values for the corresponding resulting state. So I think after all, these definitions do agree with each other. It's just that it's kind of tricky to understand without looking at the equations. You kind of like need to um, derive the equations and then look back at the verbal language description to make sense out of all of it. And if we look back at my kind of like intuitive understanding of the Bellman's principle, I said, if if like a control sequence is part of an optimal sequence, um, then any optimal sequence will contain this claimed optimal sequence. Well, it's partially correct, but it's missing a few, details there. What I really should have said is that should be that if a control sequence is part of an optimal sequence U, um, for for a state, right? Let's just write it down here. Yeah, for for some state xk, right? Right, xk to I guess xf. Then any control sequence, um, you know, that that passes xk will definitely contain that sequence. And well, instead of saying part, we're gonna say is the optimal, not part, the optimal sequence for that, then any optimal sequence that passes to xk will contain sk, and that makes sense now. So let me just make this a little bit more readable. If you do end up looking at this document, I'm gonna say is the optimal sequence u is the optimal sequence u for this, right? Now let's remove this for this for xk to xf. Then, right, I'm gonna move these things a little bit to the right. Then any optimal control sequence, um, yeah, maybe I should say, because it's weird to say like a control sequence that passes a state. We should say optimal control sequence and state sequence uh, that passes xk will contain this control sequence. Right, so maybe I should also change, the yeah, the use of, I guess, letters here too, because S is confusing. I'm gonna just use capital U to mean the sequence of U. Right. And what is this U here? Um, yeah, it's kind of like any U, any optimal U that goes from any state uh, and then passes xk. I think fine. I mean, this. I guess I did my best to try to make this definition make sense. So I'll just leave it like this. Yep, I think it's good enough. And yeah, so this is like my personal version of what Bellman's principle is, and I can just derive the optimal cost to go calculation from this definition just fine. Uh, so I'll take it as an okay-ish definition because it is this recursive calculation relation that matters in the end. So that summarizes today's problem, and we have again implemented a Bellman principle to calculate, the minimum cost for a certain procedural activity. In this case, it is climbing stairs. We implemented code that is similar to one of the solutions, the solution approach number one, bottom up, bottom up dynamic programming tabulation. We implemented in Python. The solution did it in Python 3. And somehow, for some reason I don't know yet, the solution is a bit faster than mine. So maybe in a future video, we're gonna, retrospect a little bit and find out why ours is like slower than the solution, although, all the syntax seems to be identical. So that's something we will find out in a future video. So again, thank you for staying and sticking with me for about an hour and a half. And I'll see you in our next video.